All right, welcome everyone. So in this video, I want to walk through a concrete example of how we can orthogonally diagonalize a matrix A. And here our matrix A is symmetric. And so recall we just discussed that a matrix is orthogonally diagonalizable if and only if it is symmetric. So since matrix A is symmetric, I know I can orthogonally diagonalize it. And just to recall what that means I'm going to be able to write A as a product of P times a diagonal matrix D times P transpose, where P is an orthogonal matrix, meaning that P has columns that are orthonormal to each other. So the general steps involved are going to be, we're first going to find the eigenvalues for our matrix A. Then for each eigenvalue that we find, we're going to find a basis for the eigenspace of each of those eigenvectors. And if those eigenvectors all happen to be orthogonal to each other, then great. We've already got our columns are orthogonal, and we just need to normalize them. If these vectors that we've listed in step 2 are not orthogonal, all of them are not orthogonal to each other, then we'll have to go through that Gram-Schmidt process. And then lastly, we'll normalize each of the vectors so that we can construct a matrix P which has orthonormal columns. So I don't want to spend the time going through calculations for eigenvalues and eigenvectors. We've done that earlier, and there's a link to a Colab document where I've done these calculations so you can verify them. But I would encourage you to review these by hand. So to find the eigenvalues, right, we would find the characteristic equation. It's going to be a cubic polynomial that we then solve. And in this case, you can verify that we get two eigenvalues. We get an eigenvalue of -3 that has multiplicity 2. And then we also have a second eigenvalue, which is 15. So I want to note that if we had found 3 distinct eigenvalues in this first step, then identifying 3 eigenvectors, one for each eigenvalue, we would be guaranteed that those 3 eigenvectors would be orthogonal to each other. We've proven that theorem. But because we have one of these eigenvalues has a multiplicity of 2, there's no guarantee that the eigenvectors that form a basis for this are initially going to be orthogonal to each other. So let's check these calculations. So for the eigenvalue corresponding to lambda 1 is equal to -3, well, just to quickly recall how these calculations go, I subtract this eigenvalue from each of the diagonal entries. So I'm subtracting a -3, which is the same as adding 3 to the diagonal entries. So that gives me a corresponding matrix equation that says 8, 8, -4 in the first row, 8, 8, -4 in the second row, -4, -4, 2 in the third row, times some vector x equals the 0 vector. So any vector x which satisfies this condition is going to be an eigenvector for the eigenvalue -3. And so solving this equation, for example, by taking the coefficient matrix and writing it in reduced row echelon form, we see that all of these columns are just scalar, or all of these rows are scalar multiples of each other. So its reduced row echelon form just has the first row being 1, 1, -1/2, and the second and third rows are all zeros after we do some row reduction. So this tells me that solution is x1 is equal to -x2 plus 1/2 x3. x2 and x3 are free. And so writing out the matrix, or excuse me, the vector solution gives us x2 times the vector -1, 1, 0, plus x3 times the vector 1/2, 0, 1. So from that analysis, we get 2 vectors that form a basis for the eigenspace corresponding to the eigenvalue -3. Namely, one vector is -1, 1, 0. The second vector, just to get rid of the fraction, I can write this as 1, 0, 2. And through very similar analysis, we can find a basis for the eigenspace corresponding to the eigenvalue 15 is spanned by this one vector -2, -2, 1. And so now we want to go ahead and convert these three vectors to a set of orthogonal vectors. And so because each of these vectors corresponds to the eigenvalue -3, this one corresponds to a different eigenvalue, 15, we've proven, and you can check, that this first vector v1 over here is orthogonal to the vector that we used for the eigenvector for 15. And the same goes, this vector 1, 0, 2 is orthogonal to the vector -2, -2, 1. However, these two vectors that come from the same eigenvalue, these are not orthogonal to each other. When I take the inner product of these two vectors, I get -1. So we're going to use the Gram-Schmidt process to fix that. We're going to find an orthogonal basis for this eigenspace. And then we'll have an extra step at the end where we're going to need to normalize all of these vectors. All right, so let's continue this process. So far we've found three vectors. The first, W1 and W2, are two vectors that form a basis for the eigenspace of -3, and then this vector W3, -2, -2, 1, was an eigenvector corresponding to the eigenvalue 15. So if we just want to diagonalize matrix A, we can. So this would work as a matrix P. Here's our corresponding diagonal matrix D, and then we would need to find the inverse of this matrix P. So that's where the computational work might get involved. So maybe it's going to be easier to go through Gram-Schmidt on these column vectors and then save trouble, because finding the inverse will just have to require us to find the transpose of our matrix. So the problem that we have here is that these two eigenvectors came from the same eigenvalue, and therefore they happen to not be orthogonal to each other. So the Gram-Schmidt process says, well, let's first choose this first vector, W1, as our V1. Great. Now we're going to try and find a second vector, which is going to be orthogonal to the first one and still span the same space as W1 and W2. So what we're going to do is find the component of W2, which is orthogonal to the first vector. So we go ahead and we find the projection of this vector W2 onto our first vector V1 using the usual weight that we're going to find the scalar C1 by taking W2 inner product with V1 and divide that by V1 inner product with V1. So here we get that the inner product of W2 and V1 is -1, and the inner product of V1 with itself is 2. So this tells me that the projection of W2 onto V1 is given by this vector 1/2 -1/2, 0. So we want the component which is orthogonal to that. So V2 is going to be W2 minus this projection that we just found. So I'm going to take W2, which was the vector 1, 0, 2, and subtract the vector 1 -1/2, 0 from it, and that gives us the vector 1/2, 1/2, 2. So here's our next vector, and you can check that this vector V2 is now orthogonal to the vector V1 that we defined over here. So I would get -1/2 plus 1/2 gives us 0. And then our third vector we already have, because this vector W3 corresponds to a distinct eigenvalue, 15, so it is orthogonal to both of these two vectors. So now we've got an orthogonal set that we can use to form another possible matrix P. And using these three orthogonal columns, okay, now we have another possibility for this matrix P, but these vectors are not unit vectors, so we would still need to calculate the inverse of P, and it's not going to be as simple as just taking the transpose. So one last step is going to be, let's normalize each of these column vectors so that this matrix P is an orthogonal matrix. All right, so now we have our orthogonal vectors. V1 was -1, 1, 0. V2 was 1/2, 1/2, 2. And V3 is the same as W3. That was -2, -2, 1. So then we normalize these vectors. So for example, v1 has length of square root of 2. So the first column I'm going to scale by a factor of 1 over root 2 to give me minus 1 over root 2, 1 over root 2, and 0. And then we do the same for v2 and v3. So you can check that the second column, square root of 2 over 6, square root of 2 over 6, 2 times the square root of 2 over 3. This is a unit, has unit length. And if we scale the last one, w3 has magnitude 3. So we're going to scale that by 1 over 3. So the vector minus 2/3, minus 2/3, 1/3, that is a unit vector. Each of these columns is orthogonal to the other two. So this matrix P is our orthogonal matrix, which is going to give us the orthogonal diagonalization of this matrix. So now we can check that this matrix A, which was symmetric that we started with, we can write this as the product of an orthogonal matrix P times this diagonal matrix, and the ordering here depends on the ordering of our columns. So the first two columns of P were eigenvectors for minus 3. So the first two diagonal entries are minus 3. This last column is an eigenvector for the eigenvalue 15. And now, rather than take the inverse of this matrix, which is going to be really, really messy, because it's an orthogonal matrix, we know its inverse is just the transpose. So the top row is going to equal what the first column of matrix P is. And if you want to check these calculations, I would encourage you probably not to do it by hand. There's a link in the description of this video to a Google Colab notebook where these calculations are checked in Python. And I also just want to mention that this is not a unique matrix P. There are other possible orthogonal matrix P's that would do the same. And in this Colab notebook, I provided a second example for a separate way that we could have written this as a product of P, D, P transpose if we had chosen different representatives for the eigenvectors for our eigenvalues.